In Module 13, we study integration by substitution. Now, what do you mean by integration? To integrate is to find out an integral, either indefinite integral, the antiderivatives, or the definite integral, signed area. Here, we're going to use the substitution as the main technique. Here are some motivating examples here, and let's look at this kind of rather complicated integral. How do you calculate this antiderivative? We substitute the inside of a certain composite function with appropriate characters, say y, and go from there. How about something like this? We're going to take the inside of a composite function as some other character, say s, and then go from there. We're going to substitute the inside of the composite function with another character, say u, and then we're going to go from there. In short, all these are related to the composite function. And what's the derivative and antiderivative rule for composite function? It's called a chain rule, and it looks like this. Now, most of the time, I'm going to talk about the techniques and some example problems first, and then I'm going to do the theory part later because those are harder to understand and not always directly related. But this time it's going to be an exception. They are directly related, and it's going to be a little bit better to understand the technique if you know the theory first. So let's talk about the theory first here. Please be patient here. It may be a little bit difficult to understand for a lot of students, but please be patient. Let's start from the chain rule. Three-step process goes like this. Green part, the outside first, the derivative of the outside. Next, the red part, the inside stays the same. And finally, the blue part, the derivative of the inside comes not inside, but here, like a dangling chain. That was the ancestor of the chain rule, and we had been using the chain rule since week 3, week 4, and so on. Now let's look at the chain rule in the opposite perspectives. In terms of antidifferentiation, we can rewrite the chain rule like this. But first, let's begin with the derivative-antiderivative relation. Instead of starting from f and then taking the derivative f prime, we're going to start from capital F and then take the derivative and then go to small f. Or, equivalently, we can start from small f and take the antiderivative to capital F. The equivalent, and then we have been using this notation, small f, capital F notation, in fundamental theorem and before, so I don't think this is going to cause any kind of problem. Just replace capital F with small f here, and y with g, and that's going to be it. Okay, now let's apply the chain rule, and this becomes that. It's not too bad. The derivative of the composite function, step 1, outer function, capital F prime. Step 2, inside stays the same, y of x. And step 3, y prime f here, like a dangling chain. And then change this notation, capital F prime into small f. And y of x, the right part, stay the same. And y prime, the chain part, into dy dx notation. Now, does it help? Yes, indeed, it does help. This is equal to that, and then we're going to take the antiderivative of both. So we have antiderivative of the derivative, so they cancel each other out, and then we get the original composite function, capital F of y of x. And in the right-hand side, we have rather complicated antiderivation here. Integration of f of y of x, and then times the derivative times dx, like this. This is the reverse chain rule, the antiderivative version of that. And then this is basically an intermediate form. Now, how do we apply this? We're going to apply it like this. If we have rather complicated integrand, it's going to take a bit of effort to decompose into composite function times the derivative function, but we can do it. And then once we do that, then we can rewrite this integral into much simpler integral like this. No more composite, we can apply the antiderivative rule directly. Okay, how do we actually apply all this into a motivating example? Let's do that, but before that, okay, let's put this over here so that we can utilize this. Alright, let's begin with this problem. Let's get ourselves ready. Now, this is the inside of the composite function. So let's color code it into red, just like here. And then this one, dx part, as you can see, dy dx, that's the derivative part. Let's color code it into blue. And this color coding will really help. Okay, let's go. First, the substitution. Y equals 16 plus x squared, the inside of the composite function. Next, we take the derivative. What's the derivative? Derivative of 16, that's 0. Derivative of x squared, that's 2x. And finally, we solve for dx. So, solving for that, let's take the intermediate step as a matter of fact. Flip this denominator to the other side. Okay, alright, now let's solve for dx. Flip this 2x the other side. Okay, are we ready? Yes, we are. This is the initial substitution. Here's a reminder. And we did some derivative computation here because the chain rule has derivative. And then dx is equal to 1 over 2x dy. It's a little bit difficult to see why if you look at only the first line, but if you counterbalance with the second line, it's pretty obvious what to do. The red part will become y, and this dx will become this blue, 1 over 2x dy. Why are we doing that? That's going to become rather clear in the next step, so please be patient. So 16 plus x squared, that's y, okay. And then times, and then instead of dx, I have to multiply that one over there. Oops, I lost the color. I don't know what happened. Okay. Now, is this better integral or easier integral? Yes, indeed. I hope everybody can see that x here and x there cancel each other out, and eventually you're going to end up with much simpler integral like this. X is gone, and then this x is gone, and then this 1/2, I can always pull it outside the integral because this is just a coefficient. What do we have now? This is just a y integral, and it's just a straight ahead power function. It's very, very simple integral. Go back to this. This was hard. Not anymore. This is easy. And this simplification process is basically the purpose of all this computation here. Substitution and some derivative computation, solving for dx. Why did he do that? After doing those substitution in, we have appropriate simplification, and we are supposed to get much simpler integral. Let's finish this computation. So we have the antiderivative of y to the 1/5 power dy, and let's finish this computation, times y to the raise the power by 1, and then we have to divide. This is good. This is correct antiderivative, but it's not the final form yet. The original problem was given in terms of x. This is correct antiderivative, yes, but it's given in terms of y. So let's simplify, or let's take one final substitution. Excuse me, I mistyped this. Okay, a little bit of simplification here, and then this y is 16 plus x squared again. And there goes the full computation. Let's recap this a little bit. Rather complicated integral here, but this is a composite function. So we take the inside of a composite function as another character y. That's substitution number 1, which is highlighted in red here. And then look at the chain rule here. We need the derivative, dy dx, so we do the derivative computation. dy of dx is the derivative 2x, and then some algebraic manipulation. Flip the denominator to the other side and then solve for dx. Why? Because we have dx over here. We want to replace it with a y expression. And we do that. The blue part substituted in place of dx. The red part substituted in terms of like this. And then some further simplification. In the end, all the x expression disappears. And then what we have rather simple y integral to calculate. From this point on, just piece of cake. Antiderivative computation and a final substitution. So substitution number 1, derivative, solve for dx. Substitution number 2, the red part, blue part. Antidifferentiation and substitution number 3. That's how we handle the integration by substitution. We have a full solution here in my notebook, and I don't need duplicate solutions, so I don't need these anymore. And here, you can review with my notebook here. Now, we don't have time to do another problem in this video, so we'll come back and do more video. I guess we're going to have to spend maybe 3 or 4 more videos on integration by substitution.